All right. So welcome everyone to this edition of this monthly edition of the EuCAPT colloquia. Today it's a great pleasure to have Guilhem Lavaux speaking. Guilhem is a research director at CNRS at the Institut d'Astrophysique de Paris, and he's a specialist of the large-scale structure of the universe. And in particular, he's one of the leading figures in the field of Bayesian field level inference and high performance computing for large-scale structure. And today it's a pleasure to have him speaking about the Manticore universe and applications to cosmology. So Guilhem, the floor is yours.
Thank you, Sébastien. So indeed, I'm going to present some of the last results that we have in a big program that we started more than 15 years ago now, related to the building of digital twins of the universe in the computer. So a universe in silico from the large-scale observations of our universe. And the point being that we want to test physics as much as possible in all its details, as far as we can go, and of course it's extremely massive entertainment, a massive approach to all this data assimilation and processing. And I will only present one part of it, and even if we'll see that maybe we have time to present even this fraction. So before actually starting, so it's as I said, so it's actually a large effort, collective efforts by many people. So there are many PhD students and postdocs that worked on this for the last 15 years. It's actually not even completely exhaustive, but this one is the most of the contributors for this session. And they collect all the development of Borg and all the analysis that were attempted for the cross-correlation analysis that I will present. So the actual outline presentation will be fairly short, in big bullet points, because I will go back to what is Borg, how it's related to the Manticore, because Manticore is a data product and Borg is a software. And they're all related to an idea of how to explore the universe without relating to summary statistics as much as possible. There is still summary statistics involved, meaning that we have to compute some compression of the data. But what we want is really to produce observables as you would have in a research lab environment. But this time your lab is a universe. So I will highlight a few of these applications. So there's the last one actually will be about some dark matter constraints from an earlier work in 2021. But the most recent one will be on the velocity field analysis of the universe, the H0 inference, and some analysis of galaxy and cosmic structures like galaxy clusters with the CMB and X-ray and the cosmic voids. So first, what's from a technical point of view, what's a Borg software? So it's a kind of the main component of a Bayesian large-scale structure inference pipeline, for which we try to take observations. So that's would be galaxy surveys, for example, galaxy spectroscopic surveys, like here, galaxy shear surveys, but it can be even other kind of data. At the moment, that's two main applications that we attempted on data. And the point is to generate the pyramidal fluctuation influence of our universe. So really the modes that constitutes, for example, the random mode that is at the output of the inflation epoch, or even the pyramidal density post-inflation, if we don't manage to actually do all this forward modeling even during the inflation epoch. To do a cosmological inference in terms of parameters or even model. And to have a flexible galaxy bias model so that you relate what is your matter fluctuations that are on large scales to actually the tracers that you have in your surveys that are galaxies or even the shape of galaxies for galaxy shear. So these are these are more empirical, the galaxy bias models, and still an open area of research. So we have some choice that we had to make. The output of this software is actually a Monte Carlo Markov chain, because it's going to explore the parameter space that available, which is both a parameter as a model, but as a parameter also in terms of initial conditions. What are the actual fluctuations of your gravitational field that generate point by point the structure that you form in your universe? And this is actually, this is a part that is very computationally involved because as you can imagine, so you have a huge degree of number of degree of freedoms available, principal and infinite number, but of course we limit ourselves to a finite. And even this one would be like in the billions at minimum of modes available that we want to fit. It's of course depending on some model that unlock systematic diagnostics and for the data. And it also provides some kind of self-diagnostics. That means that if we have some idea of what the model that we understood the universe is behaving, so let's say that from the CMB observations, we know that some parts of the cosmology shouldn't like vary too widely outside of a lambda CDM scenario, or at least within a lambda CDM framework. Then we can actually give hints to the machines to not, let's say, go too far away in the model space. So, of course, for this we have to use, there is no way around it, Bayesian formalism. The Bayesian formalism, as a very quick reminder, of course, and to set down like the language, is that we have the a priori knowledge on both cosmology and the initial conditions that we want. That's going to be into this function. The data likelihood, that's how we explain or how we can give the envelope of how we understand the data that is generated, that is observed through like the different missions. And what at the denominator is called the model evidence. That's the evidence of the model that we have, that we use for all explaining of these data sets here. In X, of course, we have cosmological parameters, but they have also initial conditions that go into it. The data itself could be galaxy positions, microwave temperature, the shear, etc. So Borg is a probabilistic inference problem, meaning that you're going to actually give, like, you want to explore like a full posterior. For us, for the rest of this talk, actually, we'll work at fixed model, like lambda CDM. To some extent, like some limited number of cosmological parameters, even if it's allowed to actually leave them free. And we run, of course, at fixed data sets. So that's what you observe. And the X, the initial condition that we're going to sample are going to be produced as part of a Markov chain. So you may be used to have, for example, a few parameters for when you do cosmological analysis, but here all elements of your Markov chain will be a full cubes of your universe that can span like a gigaparsec of observations. So to give an idea of the effective challenges, so if you have like a data set that looks like this, that in practice what could be like fluctuations in galaxy counts between 0 and 3 in these voxels and with units of megaparsecs. The signal that we're after is this kind of thing. So of course we only see this, and we would like to recover this exactly. This, of course, we use the Markov chain, so we are going to build like an ensemble. So that's and replace the posterior distribution by a Monte Carlo ensemble of elements, and we are going to compute summaries of these posteriors using this representation. The Borg software is actually sampling initial conditions through a loop, for which you have like both like systematic effects and bias that I mentioned here, like this phenomenological bias that I will come back to it in details in the second part. For this, we have to freeze some aspects of the bias model, and so for which we can sample like parameter space of the cosmology, for which you freeze the cosmological parameters, for which allows you to sample like other systematic effects like the bias, and then you sample initial conditions at these frozen aspects here, so that you can have like a more efficient exploration focused on initial conditions. And in practice, for all these atoms, you go through the full chain, meaning like you start from these fluctuations that you simulate with an n-body solver like a full n-body simulation that span like the volume of interest. You repaint with a small-scale gas physics. You inject like cosmic expansion, and you compare to the observations with a likelihood that has to be designed adequately for the instrument. So we are going to focus on this part here, so the initial conditions, that itself like is done with what's called an Hamiltonian Monte Carlo technique. So the Hamiltonian Monte Carlo technique cannot be achieved with any kind of simulator because it needs like to backpropagate the gradients of initial conditions, meaning that we need to know that for given fluctuations of the data, or how it's propagated to a fluctuation in initial conditions. And that's how it can achieve to have like an efficient exploration in the billion parameter space of this parameter set. So this is what we started like in actually with other groups in 2012, 2013, and we progressively increased the complexity and the parallelism of the software, so that, and the flexibility of the model that we want to achieve, so that it can run like at scale and absorb like modern data sets. So in practice, this code is here, and it's available if you want to use it maybe for like a new survey experiments. I encourage you to contact us. So in detail, so that's again, so we want to simulate these surveys, and there are all these parameters. I glossed over like some of the details of the model that are part of this chain. So notably, there is a first part that would be like a perturbation theory. So we are using a linear modeling, Lagrange perturbation theory at different orders, including like modifications called like quantum Lagrange perturbation theory, for make like the early formation of a large-scale structure a bit more easy. We rely on the n-body simulation that's called like a particle mesh, or like a variance, for which you accelerate this particle mesh by using specific coordinate systems that lives on the Lagrange perturbation theory that you specify here, so that you can do only n-body simulations in 20 to 30 time steps. So that is still tractable to run like on large supercomputers. And to some extent, if we want to play like more like a machine learning game, so we have also a model that's based on neural networks, so that it can transport from a perturbation theory solution to a model that has been trained with a full n-body simulation. So that's something that I will not talk about, but that exists, and we can discuss about. The outstanding challenges that I will come back to in the next section is the problem of galaxy bias. As I mentioned, it's an empirical model, purely empirical. There is some information that exists from like the use of n-body simulations and from the decades of observations with survey data, but they are still like a blocking point. And again, what I must instate is like Borg needs a differential generative model to be efficient to explore the parameter space. And of course, because it's an explicit model, we need an explicit stochastic model for the likelihood. For us, we are going to focus a lot on Poisson likelihood. So Gaussian has been explored as well, but it's only true for like correct for like extremely large scales. For the kind of example that I will come back to, so we focus on the Poisson likelihood. Okay, so I will now go into a lot more details onto the Manticore inference family. So Manticore is a data product. It's a specific choice of model that we decided to go after, and that use the Borg model in the spirit of generating like an ensemble of data that could be then correlated with also observations. So the point is to build like an ensemble of digital twins of the universe. And so first, we want to pass like strict posterior predictive test, meaning that we want to be sure that when you get like your digital twins as resimulations, it looks as much as possible in terms of summaries to something that pass the previous experiment. For example, if the CMB tells you that the two-point correlation function should be within some limits, then we want to pass this test. If the galaxy clustering on large scales are within some limits, we want also to pass this test. So we don't want at the moment to be to explore like too exotic models, and that would come later on when we are more sure that the model is robust. So it allows some also some more other kind of validation. So basically, if we look at the resimulation that will be unlocked by this model, that we can really look at population levels of your galaxy. So for example, if you resimulate and you find out that you have some galaxy with some properties, you can really focus on this area and be sure that your model is as predictive in some part of your volume as in any other kind of environment. And it allows you to distinguish a bit model failure from systematic effects to some extent. The point of this Manticore data also is to unlock some potential discovery for hard to observe properties. So for example, if you do a velocity field, so that's typically a data set that are extremely difficult to model and to understand in details. So the Manticore provides already a base, and I will come back to it, so that you can do a comparison, safe comparison to KZ maps or to distance data. The tidal fields that are also unlocked by the Manticore data could also like trigger also the kind of effect that are available in CMB. So like for example, moving lens effect. The matter density can tell you about lensing effect. The formation histories of halo galaxy clusters to give you like ideas of formation of galaxies. And optionally, once you have your large volumes, you can decide that if you want to do more focused observations, then you can optimize your survey strategy. So that's also a way of having a playground before going to real data. The inference family as it exists nowadays is composed of 3 to 4 actually examples. So the 3 is like the Manticore Mini, which has a size of 500 megaparsec. The Manticore Local, which is 1000 megaparsec of size, with a constraint that is 250 megaparsecs. So the actual observation is within this cube here. And the Manticore Deep that is much larger at 6000 megaparsec, with like a constraint that that covers a redshift range of roughly 0 to 0.7. So here it's in megaparsec, and here it's the units of megaparsec over h, just to be clear. The first step here that I will skip the Manticore Mini because it's basically just a slightly higher resolution of higher like focused volume than the Manticore Local, and it uses the same data set. There is also other variants called like the Manticore like local group, which focus on the galaxy, the local group of galaxies, meaning like Milky Way and Andromeda. I will not talk about it either. And there is also another one that exists at the Quaya set that will come like public within, hopefully within a few months. That is much larger than this one, the Manticore Deep. So Manticore Local. So Manticore Local is using 2M++. So 2M++ is a galaxy compilation that I made like in 2011 with Mike Hudson. And the point of this compilation is that it's fairly close to full sky, and it's based on two masteries survey, the 6DF and SDSS within a volume that is fairly like intermediate from a cosmological perspective, from 0 to 250 megaparsec of range from the observer. Of course, you can see that it's not completely full sky. So depending on if you cut in bright, so that's the mask for the bright cut. It will be like indeed like close to full sky, except the galactic plane that you have here with the bulge. And if you cut at a fainter magnitude, you will not have access to this part because there's no telescope that was getting the spectroscopic sample in this part. So it's an interesting playground. So if you want to have something where you have access to have like a velocity field for all the local environments, and be sure that you have a bit of control on isotropy of the sample. So we went to this data set several times. So that's the third iteration, and so the third iteration is the Manticore local, and it covers like a data volume of 1,000 megaparsec. With 256 cube of modes for each MCMC, and it has used like order like 10 million CPU hours to be computed, and it used like a DES year-free cosmology as a fiducial cosmology to do the inference. The whole details are described in this paper for this one. So if you want to go a bit more technical for the model, so we use the class model. So class is developed by Guilhem Lavaux and company. And we didn't inject any neutrino because we don't expect to have a lot of sensitivity to neutrino in this first in this volume, and with the noise, the shot noise in this data set. The dark matter evolution, so we use this T-Coda model, which is this co-moving Lagrangian acceleration, so that allows us to have only 20 time steps to reach redshift 0. With the force resolution sufficient to form like sufficiently well like the big groups in your volume. So meaning big groups, meaning like objects of 10 to the 13, 14 and up. We injected like redshift space distortions, meaning that we can model correctly, like at least a Kaiser kind of effect on large scales. And the bias model, as you can see, is empirical, and it's a bit, it has like 3 components. So it has a component that's a bit, that relates like the matter fields to the galaxy count fields through a power law. A sigmoid component that's going to inhibit completely the formation of galaxies in voids. And another one that actually redresses a little bit what's happening in cluster. So, and it's also a local in mass transform, meaning that it takes like a mass that is inside a voxel and transform it into a galaxy count. It doesn't care about the outside world, except for like the evolution that is triggered by the n-body solver. If you have questions like those, specifically, don't hesitate to ask afterwards. What's very difficult, of course, it's this model is that we know it's going to break. So it's definitely not like a correct model for the formation of halos or galaxies. But we have a pretty good idea that lambda CM should not be too far from a correct solution, at least for this survey. For large surveys, maybe there would be deviations, but that's still to be explored. And so we needed to have a way of teaching the machine to penalize the galaxy bias and not the cosmology. So we needed to. So in the end, so we enforced 2 things. So first, that we need to have a white noise for the generation of the initial conditions pre-inflation. And that's a point of this first term here. And the second point that we wanted to have like the 1-point statistics that is in agreement with something that is a pure white noise also, that without like a skewness, kurtosis, and with a variance that is within some reasonable agreement. So we enforce this as a part of the prior description inside the machine. So then we went to see if once you do the inference, if the actual white noise is actually has the correct properties. So here it's a white noise pre-inflation. So before we colorize the density with class, and so this is expected to be within 1, and indeed, so these are like the standard the cosmic variance limits. And the mean fluctuation here indicated by these blue lines is within what we expect for the universe. So it looks like a white noise after we injected this additional component. So is it physical? Meaning like what happens if we simulate this with an n-body solver? So if we take a random lambda CDM universe, that's this orange line that we have here. And if we take like the Manticore local parent volume, that's also like for the power spectrum behaving like we want, with including like the BAO features that you can see here, up to the Nyquist frequency. The bispectrum also is within what we expect, and the halo abundance is exactly following what you expect from a random lambda CM scenario. Even though you can see if you're like very picky, you can see that there is a little bit of 5% like decrement that might be related to a slight underdensity that you have like in the local environment. So that's the first step that we run for this Manticore local. I will come back to like a further test that we did, but this time for like galaxy clusters and for the velocity field in the application section. The second part that we wanted to highlight, that of course once we got this into control, there is also a Manticore deep. So the Manticore deep is much more interesting if you really want to explore like a deep lensing and correlation with CMB, for example. Because instead of focusing on this 2m++ that you can see at the focus on the central part, so you have also access to the SDSS here that covers from the redshift 0 to redshift 0.2 to 0.3. And the low Z thing that's between SDF for the SSS 3 that cover 0.2 to 0.4, and the CMAS that is 0.4 to 0.7 in redshift. So all this represents like a volume of 4 gigaparsec. So of course it's a much larger endeavor. So the Manticore local was 1,000, but the Manticore deep is 100 times the volume. And it has also different kind of bias properties. It has like lots of different. It has also Lycon effects. So we have like to wrestle these aspects. Just to showcase a little bit. So that's the initial n-body resimulation that we obtained on the Manticore deep after the inference, and it's after. And it's 27 inferences twice because we wanted to have reproducibility. It's 100 times the Manticore local, and it has about like 30 independent samples. It's not something that you want to do like every day because it is consumed like around like nearly 100 million CPU hours to compute. So just to give an idea also here, so we have the SDSS galaxies, so all the galaxies in red. And if I'm coming back here, and the inference in the terms of density that is showcased here as a mean density in the background that covers 5 gigaparsec. So here you have sees like the two kind of big elements of the big inference element of the Manticore. So what we want to do now is to see how we can use this to do physics. So there are several things that we consider. So the first targets was to do galaxy clusters because they are like much evidence. So they are very close by, very well studied objects, and notably for the local environments. So we have a bunch of clusters like this, and so notably Coma, which is very well studied in the sky. And we wanted to know if we could like find them at the correct places, if they have the correct masses, and if they match in terms of X-rays, SZs, and all these kind of properties. So we went to hunt into the volume, and we needed like to have like an halo matching technique. And the one that we used was like advertised by another group within the slow close collaboration. For which you take like an observed galaxy cluster, and you want to know what's the probability that if you take at some distance r and for some mass of this estimated mass of this cluster, that you have by chance a simulated halo that is exactly as the same as some distance and some mass. This probability is basically giving us a null test. Meaning that if it happens by chance, that okay, we don't care, it's not like a proper matching. But if it's really unlikely that this one is there for this random position in the volume, then it means that we have a good match. So that's a metric that was introduced by Pfeiffer et al. 2023, and that we reused for doing our matching. And that's this curve that corresponds here. So more in detail. So for example, if we have we start indeed for this observed galaxy cluster here, and we have like a bunch of candidates around here, then we basically select the one that is highly unlikely to be happening by chance and close by. If we play this game and we look at in practice in the volume, and we take all these clusters that we know, then we have like a joint evidence that they appear all at the same time with some mass that is actually in agreement with other kind of observations. So here it's the detection rate of these clusters at for close to the observed ones in the sky. So you see that basically we detect them mostly at 5 sigma in a number of cases. So nearly all cases at 4 sigma, and some of them like Hercules IE 2063 a bit less, more like at 2-3 sigma, but they are really present all at the same time in the chain. It's also they are present here like with an angular separation on the fake sky at very high accuracy, much better than what is the voxel size that we use for doing the inference. So this voxel on the sky would be much larger than actually what we get, like where is the positioning of this galaxy cluster. If we look at the galaxy cluster mass, we also observe that it's quite in agreement with other kind of probes. So we look into the literature. So that's a bunch of names that corresponds to the papers. There are even more, but that's the example that are in this plot. So there's a dynamical mass estimate from the Viragel theorem. There is X-ray hydrostatic equilibrium. There is SZ mass, and then there is weak lensing shear measurements. So you see that even though like this observed, so there are these boxes here. So even though the observed from these different probes look sometimes a bit scattered, our distributions that we get from the Borg and Manticore analysis is actually in the bulk, which is interesting per se, and it comes with actually the full PDF for each of these clusters. So there are a number of interesting elements, for example, like the coma cluster, which is fairly well determined in terms of mass here, with number of probes that are in agreement, except for example this one here, like before, which in X-ray, which is a bit different, which might be related to the fact that it's not in equilibrium. We know that it has a double core. So it could be, it's interesting that it points into that direction. What about velocity fields? So this one is even more, it was a bit challenging to come up with this model, but we went to like a bit more detailed exploration, notably through like the big work of Richard Stiskelek and Harry Desmond, and where we wanted to explore like several things. So first, if we could like do a consistent Hubble measurement, if the model of the Manticore velocity model was in agreement with distance data, and if we can like compare evidences between different models. So let me detail a little bit what we came out as a model. So this is like one of the specific variants of the model that Richard developed for comparing like the Cepheid, but it exists also for the supernovae. So if you follow me, so we have like the Manticore and that seeds information here at the level of density field and velocity field. We have information that comes from data through, for example, when you have a host, supernovae host here, you have information coming from Cepheids through like periodics and metallicity and apparent magnitudes. We have supernovae information that comes here through apparent magnitude of supernovae. We have eventually also calibrators for the distances that appears here for the Milky Way and the name escaped me, but like other kind of calibration. We have also like effective modeling that comes from So here there is not like the Telefischer, but there is like the host distance, the derivation that comes from, for example, the trip formula or the Telefischer relation. And here, like they seed everything up to like the bottom where you express likelihood between the observations and what the model predicts to you. The point is that we want to pipe all this from Manticore and the auxiliary parameters of these models and see which model like win to basically provide like evidence that we are good. So our baseline for all this is always like linear modeling. So it's something that we developed like so it's a paper Carrick 2015 with Mike Hudson. And that's a model that's used like in many analyses, like for example, gravitational wave, for shoes, for doing the Hubble constant inference, and so it's a good benchmark to compare to. And to compare to this, so we computed the evidence, piping through like all the inference that comes to the previous model, and we found out that so our original model that was 2019 was like not so good, ironically, but then we quickly improved with like the model, the Cyborg 2, so the second attempt, and Manticore local is the green one, where actually now we are more than a log 10 200 above like the linear modeling for the velocity field, meaning that for all these kind of data sets or supernovae formations, or like the Telefischer here, the two Telefischers, the three Telefischers, sorry. So we are like we have a really good description of the distance data compared to the linear modeling. That's not to say that we cannot improve further. We know we have like still like some leftovers of the order of a few hundred kilometers by seconds in the data sets, but that's already like a big improvement. So we of course as I mentioned previously, so this model is an evidence, but of course we looked at the Hubble constant, and to put like comparisons to everything, and I encourage you also to go to the Cosmoverse presentation by Harry Desmond for a more detailed like description of this effect and the derivation of H0. There is so we make like a full comparison to all the kind of inference, including the shoes, one of the latest shoes like inference based on supernovae and Cepheids, and we ended up with this kind of inference folding in like a better description of selection effects and the cosmic velocities that come from Manticore local. So you can see that there was some improvement in sort of error bars and a slight shift towards like the left, meaning it was like a big plank. So the tension is still there, but now we have I think that we have a better handling of selection effects and a better description in terms of forward model of all the of what goes into like the distance data sets. The third thing, so we want to venture into more like prediction. So what happens if we look at X-ray signals and TSD signals for individual clusters? So that's one big experiment that we are running with hydro simulations. So this time of galaxy clusters. So that's something that is pushed by Ulrich Steinweindl at MPA, where he takes like the Manticore local initial conditions and focus on a number of galaxy clusters. So here is an example on the Coma cluster. And what we want is to try to predict with the hydro with the full hydro what's the X-ray emission and what are the auxiliary emissions for these clusters. The interesting thing, of course, that Coma is not in isostatic equilibrium, and wanted to see if indeed, like we see tensions or things that would be selected by the model, but that wouldn't be seen by Manticore local, being only based on the dark matter. So to give a hint, for example, we see that there are typically when we select among all these models that are predicted by Manticore local, so the observations are more like these dots here. So it means that it selects like a subsample of all these models, and we already know that these models have in common of typically having like a small, like, a double core group, where you have this kind of neighbor to the first core here, with some kind of specific filament feeding to the coma cluster. The other kind of analysis that we looked at is, so that's done by Stuart McAlpine, that's more like a blind analysis and data, is to see if Manticore local galaxy clusters have a better calibration, provide like a better handle on how to look at the calibration between X-rays and SZ masses. So this is an example of what happens if we take one mass bins of galaxy clusters in Manticore local, and in different mass bins identified, for example, with X-rays. So Manticore local mass bins is here. The E-Rosetta mass bins are here for like the positioning of the galaxy clusters and their grouping. The MCXC is here, and that's a null test to see that indeed we don't see galaxy clusters if we take a random position. The interesting thing here is that we can redo like the mass profile of these galaxy clusters by doing these different mass bins, and see if there are like differences if we take this kind of different probes. And indeed, like if we can also compare like this different mass estimate and see that, for example, the E-Rosetta median mass estimate is in better agreement with Manticore local mass estimate for these galaxy clusters than the MCXC mass estimate, which could be interesting to compare to, given like they are both used for SZ analysis. So there's also, we are trying to look at other kind of structures, so cosmic voids. So that's an endeavor by the Rosa Malandrino, for example, here, that she used like the Manticore local resimulations to try to identify what are the cosmic voids, the stable cosmic voids in our environment, so that we can stabilize the analysis, notably, for example, in lensing or the gas pressure inside these cosmic voids, through like a very certain identification. Because as you can see, so typically for a galaxy cluster, that's easy to isolate, like you have a group of galaxies and you're focusing on this, and there will not be like too many fluctuations. But for identifying cosmic voids, first, that's very extended in the sky. There could be a large uncertainty linked to a mask and galaxy bias effect, and its relevance to actually have a way of having a certain voids that you can then cross-correlate to other kind of probes. So she built like a statistical framework that allows you to identify these voids here on the sky that you can see that even like interpret through the galactic plane, that give you the 3D positioning here with a degree of certainty of the voidiness in the volume, and also give you a probability distributions of the void sizes for each of these individual voids. Everything here is available publicly for everything that I said here for the cosmic voids. So to give you an idea how it looks like also in 3D, so that's a cut within like the one void that is here, and unfortunately this one is not animating, but it gives you like different cuts inside this void, and you can see that it follows actually the visual shape that you can see from these filaments and galaxy clusters. There was another one, last application, that's actually from pre-Manticore that probably will contemplate to update with or somebody will do it for the new data set, was the dark matter detection and characterization. So that's something that we did with the Borg 2019 inference that I mentioned for the velocity field, notably, that use the same data set, so 2m++, but with an earlier like model description of this data set. And we try to actually correlate the dark matter annihilation and decay signal to the Fermi lat data. So that's the work that was done by Declan Bartlett and Andrea Kostic in 2022 and 2023. And So the point was to be able to paint like really like the dark matter signal, assuming like a number of boosting factors, to have like to re-inject like halos, so that we have a better prescription for the Fermilab data, and even like folding like all this marginalization and auxiliary terms. So they managed to get like across let's say limits, new limits on the dark matter disintegration, depending on different like disintegration channels through quarks and different leptons. And that was actually quite competitive compared to the dark energy survey analysis that you can see here. So these are our limits, but not yet competitive compared to Milky Way satellites bound that is here. And here was like an example of the kind of let's say signal in terms of energy that we obtained. Of course, there was barely any signal for the characterization for this particular disintegration in BB bar. So maybe now I will give you some conclusion. So let's say some achievements. So we managed to get like this Manticore data sets out with some strict posterior predictive tests. So we wanted really to have like the initial conditions to be characterized, and the physical tests on the 2-point statistics, and the halo abundance to be passing at minimum. We looked at like the velocity field inference, and actually checked that the velocity field was in agreement with distance data, and provided also a new characterization, new determination of H0. So that's work by Richard and Harry. We explored also multi-messenger physics. So one part of it is Teklan, but also Harry looked at other kind of things for modified gravity. So there was also a Greek equivalence principle test with the propagation of photons with this kind of same data sets. We looked at cosmic structures characterizations for clusters and voids, but that's still ongoing because that's a huge data set and a large number of different signal that has to be explored. And we looked at the also like dark matter annihilation decay for pre-2019, pre-Manticore from the 2019 inference. In future, we are aiming, of course, to go to Euclid and DAISY datasets to reach really like a large volume with high accuracy, to characterize if we detect anomaly, notably, for example, polynomial non-Gaussianities, to amplify cross-correlation with CMB with this kind of effects, and go full to hydrodynamic simulations. Of course, if you have ideas and you want to run like a new analysis, we have like a number of public data. So there are some links that if I put the presentation on the website. So I put a QR code here for the first for the Collab notebook that allows you to both download data and provide some basic tutorials on how to load and explore the data. There is also a Cosmic Void website if you want to explore cosmic voids. And in general, we have here it's a link to all the different data that we are trying to produce. So thank you very much. If you have questions, I'm here, and I hope that you followed and you have new ideas on exploration with this. Thanks.
Thanks very much, Guilhem, on behalf of everyone. Are there any questions, comments, ideas from the audience? Yes, Fabian?
Hi, Guilhem. Thanks a lot for the talk. I was wondering if there's a plan to also vary cosmology in the Manticore runs, because yes. I mean, some of these analysis I think it's really crucial to know how much the inferred initial conditions depend on the assumed cosmology.
Yeah. Yes, I can tell you that at least for Manticore Mini, I think, Stuart ran it on several different cosmologies. It's not the mainstream, so we haven't validated everything for these ones, but it's definitely on the radar. For the other ones, so now that we have at least a pipeline, so we can envision to actually test different kind of cosmologies for this one. So meaning like different, for example, omega matter. I know that, for example, Stuart tried omega matter equal 1 for for this kind of inference. Most of the from like discussion, but of course it's I would say offline discussion. A lot of the differences between the omega matter are absorbed by the galaxy bias model at those scales. But this is something that we definitely need to explore, like for this kind, particularly for the future surveys.
Okay, thanks.
Of course, here I didn't talk about it at all, but for the work of Adam Andrews that look at pyramidal non-Gaussianities, so there the cosmology is varied for FNL, and he's trying also different kind of cosmology there to assess the robustness of the signal.
But this is a different model, right? This is a more simple.
Yes.
Right.
Yes. That's this one.
Can you quote any of the results you just mentioned about FNL?
Well, yeah, it's in the papers, but there is no test on data yet. It's a test.
Oh, you mean this is a proof of principle?
No, there is a proof of principle, and there is one that is. There will be a paper soon about end-to-end test on Halo mock data.
Okay.
So this one is there. It's nearly done, but there are still a few nails to the coffin to be put.
And well, can you at least say if you are concerning only FNL local? I guess you are not going equilateral or.
No, we are not playing more games at the moment on this. So we want to have the baseline at least working properly. Particularly also because there is not many simulations in the markets that have other kind of FNL. You need a generative model for that, and typically people are running this kind of simulations with only FNL local.
Okay. Are there any proof of principle papers also on modifying gravity? I mean, you can at least in an ad hoc way, like modifying the Poisson equation.
So for as part of the Borg analysis, not yet. It's let's say under the radar, but let's say that we wanted to have the other things first grounded. But there is on the side notes for the cross correlation. So Harry worked a lot in the past, Harry Desmond, on cross correlating the warp signature, for example, of modified gravity on the galaxies, but without redoing like the inference of Borg. So it's a post-processing perturbative analysis.
Okay.
Other question or comment for Guilhem?
Can you say a bit more about what you say in the last slide about anomaly detection? I mean, what do you exactly mean there?
Yes, we want to know if, for example, there are like a number of claims typically for big galaxy clusters or structures. For example, I have in mind like this Vela galaxy cluster or supercluster, or the Quipu supercluster, and see if actually these objects are really like anomalies or just part of the cosmic web. I mean, of course, the more usual one are like the Sloan Great Wall or like the Great Wall. They are like typically like quoted like a big structures that looks like sharp on the sky, let's say on galaxy survey sky, and they are like claims that they are like outliers, and we want to know if they are really outliers once you fold like the entire analysis, and with including like selection effects. And at least so far we haven't seen any kind of anomaly in this respect. So whenever you measure back this, so it's just in the mean of cosmology. The other kind of anomaly that we want to characterize is, for example, I mean, this one will be more in the observations. So if, for example, for diagnostics, so if you look like an inference and we want to, if there is like a problem, so we want to know if it's an observational anomaly, that would be just, there is a problem with the survey, or if it's a physical anomaly, so we are working on machines that can distinguish between the two.
Other question or comment?
What is your first target? You are going into hydro simulations, so that's there. You're going to be even more CPU bound. I mean, obviously,
Yes.
no obvious shortcuts like Lagrangian perturbation theory, Ticola, and all that. So you have to restrict your goal. So what is it that you want to assess in priority?
Yeah, so at least for what they want to assess with the TNG model here is like whether it's already a good prescription for all the galaxy clusters that in the Manticore local, meaning that if you take individually and then need to take like this kind of two signals, at least that are average along the galaxy clusters, if it's portable and universal. So doing these zooms is not too expensive. So that's why they can run at least like 50 simulations for all these galaxy clusters, and at least for a fixed model. And then they will think about like varying the model to see if they can account for these discrepancies. For galaxies, so we are more aiming towards using summitic galaxy formation model, which are much cheaper to run, of course, but still expensive because you need merger trees. So I alluded somewhere, I forgot where it is, somewhere before, yeah. So so we have like a number of simulations. So for the Manticore local, so we have also a variant that is much higher resolution in a zoom that allows you to make like merger trees at the level of 10 to the 12 solar masses to really have one for Milky Way scale galaxies for the entire volume. Meaning that then you can repopulate this with summitic models with varying like their parameters and test the universality of this model for different environments and their predictability for different kind of wavelengths. Yes.
Yeah, no,
we were thinking also, but so we have people thinking of the supernovae, of course, like the influence of the environment, because it's a big deal if you're if you want to measure H0 and cosmology, if there's like a dust contamination. So if you have environmental effects, so that would be that's typically a good playground for them. So they are looking into it.
Mr. Chairman, may I ask a final question?
Sure. And I still have one.
Okay, so what's the competition? I mean, these are expensive universes, and you are sort of catch-all. So what are you up against?
Competition in terms of groups, or in terms of
you define it. You are racing with whom?
For the moment, we're racing with ourselves.
Excellent. So you are ahead.
As I mentioned, so this model, so there is a much better where is this? So here, so this comparison here, so there is a much larger competition. Comparison of model that exists that was published by Richard in 2025A and B, or 25A, sorry, between different kind of models. And for the velocity for Manticore local, at the moment there is no question. The best model by this amount of order of magnitude is by 400, let's say, of 10 to the 400, is Manticore local. For all the others, even like if you take it jointly, at the moment, I don't see that the others are like at the level either. And there is no other yet application that I'm seeing for the thing that I mentioned for galaxy clusters. And that's why actually there is a big program that we are thinking of developing with MPA for having a full full resimulation of this at the scale of, I mean, for the full volume, I mean, with Illustrice TNG or the new model with this kind of initial conditions. So I believe that we demonstrated this within our collaborations, and now the point is that we want to continue improving in volumes so that we can have several probes for CMB and shear lensing, and to try to improve still this galaxy bias model, because if we can stabilize this one to be sure that it's stable with an end-to-end test, then we can open up cosmology inference in the machine, which exists formally in the software, but which don't want to open it because we know that there will be lots of misspecification due to this effect. And then we can try to test this to apply it to, like, for example, like the future data of DAISY and Euclid.
Yeah, how confident you are that when you increase the volume sample, that is the time span, your bias model will remain correct? Because if you're exploring earlier phases, you may uncover some new aspects, isn't it?
Yes. So for Manticore Deep, so where's this guy here? So if I go back to, let's see this one. So actually, this one is not a single volume. It's actually a tile of 50 volume, or 50 or 25, forgot. And each volume is independent in this galaxy bias. So, and independent for each piece of survey, meaning that you take CMAS, slice in luminosity, and in piece of volume. And this one each galaxy bias is independent in each of this. So it means that it's already pretty a big parameter space that you're throwing into the inference.
But I didn't realize that. So how consistent this is? I mean, how can you tell? I mean, not if you're essentially sampling your galaxy bias in different ways, in different volumes, what makes sure that this is not a completely crazy bias story versus redshift? I mean, because
it's a phenomenological model, of course. It's from the start, it's phenomenological. So maybe
but you can explore. I mean, you can sort of say then something like in a certain mass range and so on. How does this? How is the bias evolving with redshift, and see whether it's having some wiggles or things which are completely crazy. That's what I'm fishing at.
Yes. I mean, that's up to you to go and dig into this Markov chain and see if it has like weird defects. At least for CMB lensing, when you do the cross correlation of these data sets, it's right on spot. So the matter field, at least, is not crazy. For then maybe there would be like craziness, and we need like to have people once we push this publicly, so fully within a year. Then it will be up to people to explore and see if there's like more deviations that we haven't seen.
Thanks.
Thanks very much, Guilhem. Well, I just have a naive question, or just come back. You were a bit quick for me about characterization of the voids. Can you come back to me, explain to me simply what do you do with it? I didn't get it.
So the point of first of the voids here is that it's very difficult to have certain voids, because the idea. So there are two things that make it like complicated. First is that the data sets are intrinsically like systematically affected by mask and the properties of your tracers. And second is that your void identification is typically a deterministic algorithm. It's not a stochastic algorithm. So it will tell you only one answer per analysis of your simulations. So here Rosa developed technology that allows you to use the Manticore dataset that fold in like the analysis on the mask and uncertainty on tracers, folded in with also the resimulation that we do on this, you analyze with the VID framework, VID, the void identification toolkit, to give you like an ensemble of voids and isolate the one that are recurrent in the Markov chain analysis so that you're sure that they are real voids in the universe. Then from these voids, you can use them as a baseline for cross-correlation analysis. So for example, it could be ISW, could be for dark energy exploration. It could be SDs for gas pressure analysis, or it could be galaxy properties if you want to isolate whether the one that are a bit deeper in voids are going to have different properties from the one that are like on the outskirts of voids. This is something that people have looked at for like very deep samples, but first they had to throw like a really deep and large number of voids. And second, it was a catch-all. So there were like a lot of crappy voids. There was like there were like a number, of course, you have to go deep. So it means like your tracers are not well necessarily characterized for all like different distances. Here it's like a very close by volume for which you have lots of multi-wavelengths information of the galaxies and for which you can do like a very detailed cross-correlation analysis. So at the moment, we are doing some exploration, for example, on SZs, so also on ISW, but the sample is a bit small for ISW for this, so it's 100 voids. And we are contemplating to expand this to the Manticore deep dataset, which will have like a really exquisite large number of voids and sufficient lever arms to explore like lensing and ISW.
Thanks very much. That was clear. Any other question or comment from people? Well, if not, let me thank you, Guilhem, on behalf of everyone.
Thanks.
Welcome everyone for coming, and see you next month for the next EuCAPT colloquium. You will receive announcement in due time. Bye everyone. Thank you,
Bye-bye.
Guilhem.